Everyone, in this very video we are going to be looking at comparison between linear and angular quantities in rotational motion. Now, first of all, we look at displacement. In linear motion we use the symbol s. In angular motion we use the symbol theta. Then look at speed. In linear motion we call that linear speed, which is v, and here we have angular speed, which is omega. Don't forget that there is a relationship between s and theta, and also a relationship between v and omega. Now look at acceleration. We have linear acceleration a, and we have angular acceleration alpha. Then I want to also quickly look at force here. Force is equal to ma. Now the analog to force is torque. In rotational motion is torque. So force in linear motion is the same as torque in angular motion. Now I want to let us also know that there is a brief relationship. You should know that s, for example, the linear of displacement is equal to theta r. That means theta times radius. Okay, the v is equal to omega r. That means linear velocity is equal to angular velocity times radius. In the same way, acceleration, linear acceleration is equal to angular acceleration times radius. And also the same way, force is equal to the torque, okay, the torque times radius. You see, they all have the same relation. So the linear relation is equal to the angular relation times radius. Okay, so let's continue from there. Let's rub this off. Okay, so we now have mass. Now for mass, the linear, we use m to represent it, while angular we use I to represent it. Okay, so I there signifies moment of inertia from our previous video. Okay, so momentum for angular velocity, momentum we know, for linear motion, momentum is mass times velocity, that's mv. Now but the momentum, now the angular motion momentum, mass now is I, which is moment of inertia. Then the velocity here, linear velocity, is omega, which is angular velocity. Okay, so the same thing with impulse. Impulse we know is force times time, under linear motion. Force in angular motion is torque, then the time is still time. Okay, then look at work. Work is force times distance. Okay, but the force in angular motion is torque. Okay, while distance is theta. So that means in angular motion, work is torque times angular displacement. Power in linear motion is force times velocity. Okay, but in angular, force is torque, and while velocity is angular velocity here. So kinetic energy is half mv squared, but we also have rotational kinetic energy, which is half I omega squared. Okay, so that is the comparison between angular quantities and linear quantities. Angular quantities of rotational motion and linear quantities of translational motion. Okay, so we are going to see this question. What power is transmitted by a rope which is being wound on a wheel 10 meters in circumference? Okay, the circumference is 10 meters, which makes 1 revolutions per second. Now, the tension of the rope being 100 newtons. Okay, we are looking for power. And what is power? Remember, if we are dealing with linear motion, power is force times velocity. But here now we can say that our power is torque. Okay, torque times the velocity here is angular velocity. Now if you notice here, we are not given torque and we are not given angular velocity, but we know what torque is. Torque is also equal to force times radius. Okay, force times radius, or you can say torque is equal to moment of inertia times angular acceleration. So torque is force times radius. Torque is also moment of inertia times angular acceleration. Now, but it looks like the one we are going to need here is this, which is force times the radius. Now, but if you notice in this question, we are not given radius, we are only given the circumference. It says it is 10 meters in circumference. Okay, and what is the value for circumference? Circumference is equal to 2 pi r. So the circumference here is equal to 10 meters. Okay, so that means the radius now will be 10 over 2 pi, and 10 over 2 pi here means 5 over pi meters. So that means the radius of this particular wheel is 5 over pi meters. Now, what of the angular velocity here? The angular velocity here was not given, but we are given the frequency, which is 1 revolution per second. And we know that angular velocity is 2 pi times frequency, which means 2 pi times 1. And 2 pi times 1 is equal to 2 pi. Okay, so that means your angular velocity is 2 pi radians per second, as the unit is. Now, with this, we can now calculate the power. Since we know the power is torque times angular velocity, okay, the torque is force times radius. So we are going to have force times radius. The force here is 100. That is given by the tension here, times the radius is 5 over pi. Okay, now multiplied by angular velocity, which is 2 pi. So you can see that this can cancel this, and at the end of the day, 100 times 5 is 500 times 2, 1000. So our final answer is 1000 watts, which we can still write as 1 kilowatt. That's quite interesting. We see a question here. A rigid body has a moment of inertia to be 20 kilogram per meter squared. We can write that somewhere. I is 20 kilogram per meter square, and rotates with an angular velocity, that means omega, of 5 radians per second. Okay, now the first question, calculate the angular momentum. What is angular momentum? If you can remember the analog of linear motion, you should be able to remember that of rotational motion. Remember, angular momentum is supposed to be mass times velocity, but linear momentum is mass times velocity, but mass in angular is I, and yv there is omega. So that means our angular momentum is moment of inertia times angular velocity. Okay, so my moment of inertia given here is 20, and omega is 5. So at the end of the day, we get 100. So the answer is 100 kilogram meter squared per second. Okay, so that leads us to the next one, which is the rotational kinetic energy. Now the analog, the linear kinetic energy, is half mv squared. So it means that the rotational kinetic energy is going to be half I omega squared. So if we substitute value, we are going to have here half times your I, which is your moment of inertia, is 20. Then the omega, which is angular velocity, is 5. Okay, so we have 5 squared. So at the end of the day, we are going to get 10 times 25, which is 250. Okay, so the answer is 250 joules. The unit is also joules. Okay, now let's look at this question here. A ball of mass 2 kg rolls down an inclined plane, inclined at an angle of 30 degrees to the horizontal. Okay, the velocity with which it reaches the end is 5 meters per second. Okay, find the kinetic energy of the ball at the bottom of an inclined plane. Now, in our first lecture on rotational motion, I told us that whenever a ball rolls down an inclined plane, it experiences two motion. One is the linear motion and the other is the rotational motion. Okay, so let's assume we have a diagram this way. Then the angle here is 30 degrees. That means the angle of the inclined plane. Now we say that the total kinetic energy Ke is equal to Ke rotational, Ke, okay, let me say linear Ke, okay, plus rotational Ke. Okay, so linear Ke, why? Because it's translating, it's going from one point to another. Then rotational motion, because it is rotating about an axis. Now the linear here is half mv squared, okay, and the rotational, okay, plus the rotational here is half I omega squared. Okay, so if we are to substitute value, if you notice here, nothing like radius is given, but we notice something that the mass of the ball is given and the velocity with which it hits the ground is also given. But before we continue that, let's see something here. We can say this is half m v squared plus half times the moment of inertia for a sphere. A ball is a sphere. We are going to see that in the next video. Is 2 over 5 mr squared. 2 over 5 mr squared. That's the moment of inertia of a sphere. 2 over 5 mr squared. Generally, the moment of inertia of a rigid body is just mr squared. But for a sphere, is 2 over 5 mr squared. Now, while our omega here can be written as v squared over r squared. Okay, now let's rub this off so we can have space. Okay, our omega here is v squared over r squared. Why v squared over r squared? Remember that v is equal to omega r. Okay, so that means omega now becomes v over r. So in place of omega, we have v over r, which makes it v squared over r squared. You see that? So you can see that r squared here can cancel r squared here. And we will be left with half mv squared, plus here 1 over 5 times 2 over 5 is 1 over 5 v squared. You see? mv squared. We have the m v squared. Okay, these two can add. If we find the LCM between 5 and 2 is 10. So we are going to have 5 plus 5 in 10 is 2, 5 plus 2. So that will give us 7 over 10 mv squared. So you see that the total kinetic energy has been reduced to 7 over 10 mv squared. So if we have to substitute value, that is going to give us 7 over 10 times the mass is 2, okay, times the velocity. The velocity is 5, so 5 squared, okay. So that is going to give us 35 joules in total. So the answer to that question is 35 joules. If you notice, nothing is said about the angle here used. Now that leads us to the next